So when we're dealing with aqueous solutions, water is the main solvent that we use. And some good things about water that makes it ideal for dissolving salts is that it's a polar molecule. And we'll talk more about polar molecules later on in the semester when we look at Lewis structures. But for now, you just need to know that water is a polar molecule, and the reason it's polar is because it has an uneven distribution of electron charge in the molecule. So if you look at a molecule of water, one end of the molecule is negative, that's towards the oxygen, so the oxygen end is negative, the hydrogen end is positive. And this makes it ideal for dissolving ionic solvents. Another interesting thing about it is that it has what we call a bent molecular shape, so the OH bonds are kind of a bent instead of linear, so linear would be 180, but they're kind of bent due to the lone pairs on the water, on the oxygen. So again, we'll talk more about uh, water's polar bent geometry later on in the semester, but these are things that make water ideal for dissolving ionic solids. And this is what we're dealing with aqueous solutions. Anytime you see the subscript AQ, that means that that compound was dissolved in water. So if you're looking at a chemical reaction, you see NaCl, and it has AQ next to it, that means it's in solution. So anytime you see AQ, it means that that compound has been dissolved in water. And so there are a few different ways you can write it. So if you have NaCl AQ, that'll work. Or which means this as well, Na plus aqueous plus Cl minus aqueous. So whenever you see, for example, a compound with AQ, it means that it was dissolved in water, and these are the ions present. So NaCl aqueous can be rewritten as Na plus aqueous plus Cl minus aqueous. And so again, aqueous infers that it's in solution and water was the solvent. And so this, again, this uneven distribution of electron charge is what makes water an ideal solvent for dissolving ionic compounds. And so throughout this chapter, the solvent we'll be using is water. Now, when you dissolve different compounds in water, you get different results. And when you put a compound in water, what happens is that the water, which generally has an attraction between itself, so the positive of one water molecule is attracted to the negative end of another water molecule. And this is called what we refer to as hydrogen bonds. It's like an attraction between two molecules with very specific atoms. So it has to be, for example, a hydrogen and an oxygen. They attract to one another. This is called a hydrogen bond, and this is what holds water molecules together. You'll learn more about this later on if you take general chemistry too. But what happens is water is normally like this, but when you put a salt in water, the oxygen end of the water surrounds the cation. And so we say we have a hydrated cation. The negative anion gets surrounded by the hydrogens because it's the positive end of water. And we call it the hydrated anion. And so this is what we refer to as a solvated compounds when it's dissolved in water. So these water molecules surround the cations and anions when it's in solution. So again, the cation is surrounded by the oxygen atoms because this oxygen is negative, and the anion is surrounded by the hydrogen atoms because hydrogen side is slightly positive. And so they're attracted and they form a hydrated cation and anion. And so this is what's occurring in solution when a salt is dissolved in water. And so when you dissolve a compound in water, there are three things that can happen. One is that your compound dissolves 100% into ions. So all you get in the solution are ions. And so that allows electric current to pass through, and you get a bulb that lights pretty bright. Another type of set of compounds, when you dissolve them in solution, form some ions, but mostly molecules. So here, this little purple sphere and blue sphere is referred to as a molecule. So in this type of solution, you have mostly molecules and you have a few ions. And these compounds, when you put electric current through the solution, cause the light bulb to be dimly lit. And then lastly, there are other compounds that you put in solution and they don't dissolve into ions, they remain molecules. And so therefore, since there's no ions to pass through the electric current, the light bulb doesn't light up. And these are referred to as electrolytes. And so one type of electrolyte, you put it in water, it forms 100% ions, causing the light bulb to light brightly. Another type of compound that you put it in water, mostly molecules, very few ions, causes the light bulb to have a slightly dim lighting. And then the other group of compounds, you put it in water, they don't dissociate. So since there's no ions in solution, it doesn't cause the light bulb to light up. And we're going to talk about each one of these types of electrolytes and which compounds fall into each category. So remember, one category, all ions in solution. Second category is a mixture of molecules mostly and a few ions. And the third category is all molecules. And so the first category that causes the light bulb to light up brightly are called strong electrolytes. So they completely dissociate or break apart, if you want to say for a simpler term, into ions when dissolved in water. Again, they completely dissociate. So they form 100% ions. And there are three classes of strong electrolytes. One is soluble salts, which we'll touch on later. So if it's a soluble salt, like sodium chloride is a soluble salt, it would be a strong electrolyte. Oops, that looks ugly. Let's see. So sodium chloride, calcium chloride, potassium nitrate. There's tons of them, but these are just a few examples. That's wrong. But these are all examples of soluble salts that are strong electrolytes. And there's some rules that we use to determine which salts are soluble, which ones are not. The second class are strong acids. And strong acids, there's only a few of them. And you'll know it's an acid because hydrogen is generally the first element in the formula. And so these are the only strong acids that we have. So HCl, HBr, HI, HNO3, HClO4, H2SO4, these are the common 6 strong acids. So if you know these strong acids, these common strong acids, all other acids are what we call weak acids. So these are the only acids, the only 6 common strong acids. So these are strong electrolytes. So again, if you know these, then every other acid that you encounter is a weak acid. So it's very important that you remember the 6 common strong acids. And then with strong bases, these are going to be your group 1 and heavier group 2 hydroxides. And these hydroxides are the strong bases. And the reason that these hydroxides are strong bases is because these are the only soluble hydroxides. All other hydroxides are insoluble, so therefore they're not strong bases. So to be a strong base, you have to be a soluble hydroxide, which will be your group 1 cations and your heavier group 2 cations starting with calcium. And these are the only soluble hydroxides. Now when you put them in water, you see that they dissociate into ions. So some of the characteristics of their dissociation is that you have an arrow pointing one direction and you have ions as products. So the arrow means that all the reactant gets converted into product, and our product are ions. So you'll notice in all of these, the reactant dissociates into ions. And again, the characteristics of a strong electrolyte solution is you have an arrow pointing toward the products and you have ions as products. Now for these salts and the hydroxides, we refer to this as dissociation. But since acids are made up of molecules, we refer to it as ionization. So you may hear the term ionization when referring to acids because acids are molecules and then they break apart and form ions, whereas ionic compounds are made up of formula units. They break apart into ions. So that's just a very slightly different terminology depending on what type of compound is forming the ions. So if you hear ionization, it's the same thing as dissociation, which means that the compound breaks apart into ions. So for strong electrolytes, we have a single-headed arrow and we have products that are ions. The second class, and this was the class of compounds that gave the weakly lighted bulb. If for strong acids, the sulfuric acid generally only dissociates once. It's very, as you'll learn later on if you take Gen Chem 2, it very seldomly dissociates twice. So usually it just dissociates one proton or one H off to form the acid. And you learn about that more when you go to Gen Chem 2 and they talk about acids and why that's for sulfuric acid. But generally only one gets removed easily. So with the weak electrolytes, as I said earlier, these only partially ionize when dissolved in water. So that means you form very few ions, mostly molecules. And generally, it's going to be less than 5% ions, generally, for most. So this is just a general rule. Most of these weak acids and weak bases usually form less than 5% ions, but there's also there's a lot of exceptions too. But overall, they form less ions than molecules. So there's more molecules in solution than ions. And for most weak acids, this is going to be less than 5%. If you take Gen Chem 2, you can actually calculate how much of the acid ionizes when you put it in solution. So that's something that you'll learn later on. But these are the two classes of weak electrolytes, weak acids and weak bases. So for weak acids, it's all the acids that weren't listed on the previous slide when we were talking about 6 common strong acids. So if it's not one of the 6 common strong acids, it's going to be a weak acid. And so there are thousands of weak acids. Again, for most of them, hydrogen is the first element. However, for organic acids, such as acetic acid written in its organic form, it may look like this, where the hydrogen is written at the end. But for most inorganic acids, hydrogen is listed first. For organic acids, you may see it written in this form. For example, this is acetic acid CH3COOH. For weak bases, these are going to be mainly your nitrogen compounds, so what we call amines, so ammonia, methylamine, etc. So what you're looking for is you're looking for a nitrogen compound or nitrogen atom attached to a carbon, or in this case ammonia, and nitrogen is what makes it a weak base. So if you see a nitrogen containing compound that has a lot of carbon and hydrogen on it, it's going to be a weak base. So for example, if we wrote this, so this would be an example of a weak base as well. So you're looking for something with nitrogen, and weak bases are generally your what we call the compounds amines. Like caffeine is an amine, it's a weak base. Nicotine is an amine, it's a weak base because it has this nitrogen in it, and the nitrogen is what makes it a weak base. And if you want to know why, again, in general chemistry 2, we talk about why these are weak bases, which means very little of it dissociates into ions. And so when you see these in solution, they look a little bit different. So with weak electrolytes, we see that we have double-headed arrows now. So double-headed arrows mean both sides of the reaction are present at the same time. So with a weak electrolyte, you have reactant present and you have product present. And the product is still ions. So for weak electrolytes, the characteristic for their ionization is you have a double-headed arrow and you have ions as product. Again, the double-headed arrow means both sides of the reaction exist at the same time. So you have molecules and you have ions in the same time. Whereas strong electrolytes, you only have ions for the equation. So all the reactant gets converted into ions for strong electrolytes. For weak electrolytes, only some of the reactant gets converted into ions, and you're left with molecules still in solution. And so again, for weak electrolytes, you have this double-headed arrow, which indicates that both sides of the reaction are present at the same time. And you see that for weak acids, we form an H+, which is the characteristic of an acid. You form H+ in solution. And for ammonia, which is a weak base, we form OH- in solution. And we'll touch on this a little bit later when we talk about acids and bases. But acids form H+ when you put them in solution. Bases form OH- when you put them in solution. And so again, for weak electrolytes, it's only weak acids and weak bases. So soluble salt cannot be a weak electrolyte. So for example, if you have salts like sodium chloride, it has a metal. It's either going to be a strong electrolyte if it's soluble, or a non-electrolyte if it's insoluble. And so you cannot have a ionic compound, aka a metal and a non-metal, for weak electrolytes. They can only be weak acids and weak bases. And the last group of electrolytes are non-electrolytes, and these are just straight up covalent compounds. And so when you put these in solution, they don't dissolve in water, so they don't form any ions. And so we're looking at things with lots of carbon and hydrogen atoms on it. So things like sugar, methanol, ethanol. So sugar is C6H12O6. So lots of carbon and hydrogen. Methanol, CH3OH. And so don't get methanol and ethanol confused with hydroxides. So these are examples of non-electrolytes. You see they have lots of carbon and hydrogen. So earlier when we were talking about weak electrolytes, I was referring that ionic compounds cannot be weak electrolytes. They're either going to be strong electrolytes if they're soluble. If they're not soluble, they would be non-electrolytes. And so for non-electrolytes, generally we have here covalent compounds, but also insoluble salts can be non-electrolytes. So I'll put that below here. And we'll talk about how do you know salts are soluble or insoluble when we talk about the solubility rules. But again, non-electrolytes can be covalent compounds, and covalent compounds, again, there's no metal, non-metal, and it's not an acid or a base. And so again, the most common mistake is that students think methanol and ethanol, since it has an OH, it's a strong electrolyte, but it's not, because it has all these carbon and hydrogens attached to it. And so when you dissolve a covalent compound such as sugar into water, this is a different type of sugar, but we dissolve it in water, we still get this compound, but now you just see it says aqueous. So again, on the reactant side, the reactant is a solid. On the product side, it's still the same molecule, but now you just see it says aqueous. So again, we're just converting the solid into aqueous. There's no ions in solution. For methanol, it's a liquid as a reactant. When we put it in water, it becomes aqueous. So it's just saying that it was dissolved in water, but it does not form any ions. It's just methanol, CH3OH. This OH does not dissociate. And then we have acetone, which is nail polish remover. It's a liquid. When you put it in water, it doesn't dissociate. It just becomes aqueous, meaning that water is the solvent. So in all of these, you see we have carbon and hydrogen in the formula. So generally when you have lots of carbon and hydrogen, as long as it's not an acid or a base, weak acid or weak base, it's going to be a non-electrolyte. And so these are the different classes of compounds when you dissolve them in water. Some break apart completely, some break apart a little bit of it, you know, some ions, mostly molecules, and then the last one only forms molecules in solution. And so for the rest of the class, we'll be mainly looking at, or for the rest of this chapter, mainly looking at strong electrolytes, because those are the ones that we can look at in regards to the moles of ions in solution, writing ionic equations in solution. We may touch on a little bit of weak electrolytes in some of these areas, but mainly we'll be sticking to strong electrolytes. So the goal of these three, knowing these three classes of electrolytes, is if you're given a series of compounds, can you identify which one is a strong electrolyte, which one is the weak electrolyte, and which ones are non-electrolytes. So now we talked about the different groups of compounds and how they behave differently in water. Now we're going to focus mainly on strong electrolytes for a while and talk about how to write equations involving those types of compounds. And so when we write equations in aqueous solution, and by the way, the little subscripts indicating the type of physical state that the compound is in is very important when we're writing equations in aqueous solutions. So just to kind of recap, if you see the subscript S means solid, L means liquid, G means gas, and AQ stands for aqueous. And these are the different states that you can have for reactants and products. And so the equation that we've been writing so far is what's called the molecular equation. So the molecular equation, we just show the compounds in their neutral forms, or the reactants and products in their neutral form, like this. So here, this is a molecular equation. You see that the reactants and products are written as compounds in their neutral form. So we have two aqueous on the reactant side, a solid, and an aqueous on the product side. So this again is referred to as the molecular equation. Now what we can do with the molecular equation is we have something called the ionic equation. And so to go from the molecular equation to the ionic, or what they call complete ionic equation, or sometimes total ionic equation, we show products and reactants as ions. So those reactants and products that have AQ next to them, they get broken apart. So compounds with S, G, and L, here in bold red letters, do not get broken into ions. So it has to have an AQ in order to break Humpty Dumpty. So if you want to break them, it has to have AQ next to the name. So everything with AQ, we break apart into its ions. And it's better to balance the equation before you start breaking apart the ions. Because if you don't balance it at the beginning, when you get down to the end, it may cause some issues. So it's always best or preferred to balance the equation first and then start breaking apart the ions. And make sure you break apart the compounds correctly. So this 2 here gets distributed to the potassium and to the iodine. Here, PbNO3 that means there's 2 nitrate. So you got to put a 2, and the 2 comes in front of the nitrate. And again, the 2 gets distributed to the potassium and to the nitrate. So when you break it apart, it looks like this. So we have the ions on the reactant side. Now PbI2 stays together because it's a solid, and then we have the reactants or the products in ions as well. And so what you want to do is now you have what's called a complete ionic equation, and then we can factor out what is exactly the same on both sides of the equation. And that's where we get the net ionic equation. So the ions in red are exactly the same on both sides of the equation. So these are called spectator ions, which don't participate in the chemical equation or chemical reaction. They're just kind of watching as the reaction progresses. So we can actually cross these out, and what we have left is the net ionic equation. So the only ions that actually react in this equation are the iodide and the lead 2+ ions. So again, molecular equation shows compounds in their neutral form. Complete ionic equation, everything that's aqueous, we break apart into ions. Everything that's solid, liquid, and gas, we leave intact. Then we look for the ions that are exactly, and I like to put that in quotations, exactly the same. Then we cross them out because those are the spectator ions. Generally, if you have a group 1 salt as a product, that's going to be your spectator ions. So group 1 means, lithium, sodium, potassium. Those are the main ones. But if you see a group 1 salt, that's generally going to be your spectator ions. So now we're going to look at another example of this. So we have molecular, complete ionic equation, net ionic equation. So here we have another one. Here's the molecular formula. Again, it's already balanced. So we have strontium chloride, lithium phosphate, gives us strontium phosphate and lithium chloride. So this is the molecular equation. We break apart the ions. And again, a very common mistake that students do is when they break apart strontium chloride, they put this. Instead of putting 6 Cl minuses, they'll put 3 Cl2 minus. And there is no such ion as Cl2 minus. So this 3 gets multiplied by the 2 and we get 6 Cl minus. Don't fall into the trap of writing 3 Cl2 minus. There's no such thing as a Cl2 minus. So that's just one common thing that students do. So again, you break apart the aqueous into their respective cation and anion. So this 3 gets distributed to the strontium and to the chloride. For lithium, gets distributed to the 2 gets distributed to the lithium and to the phosphate. Again, you break them apart into cations and anions. Don't break apart phosphate into oxygen and phosphorus. That's a no-no. And then the 6 gets distributed to the lithium and to the chloride. And so now the ones I've highlighted in red are the spectator ions, because you see that they're exactly the same on both sides of the equation. So now we can mark them out, and what we have left is the net ionic equation. So the only ions that are reacting in this equation are the strontium and the phosphate. Now a question may arise is, how do I know that strontium phosphate is a solid? And we may not get to it in this lecture, but we will talk about solubility rules. And based on the solubility rules, you know that strontium phosphate is insoluble, and for example, lithium phosphate is soluble. So we're looking at, solubility rules to write the aqueous or the solid for the different reactants and products. And again, solubility rules may not be in this lecture, but it will be in the next lecture. We'll look at another example. So here we have magnesium sulfide and copper 2 chloride gives us copper 2 sulfide and magnesium chloride. And again, those reactants and products that have the aqueous need to be broken apart. The solids stay the same. And when you break it apart, you have to have the right ionic charges too. So here sulfide is a -2. Magnesium is a +2. Don't fall into the trap of putting +1, -1. It's +2, -2. And so here, when we write the ionic equation, all the reactants are ions, and on the product side, we have copper sulfide, which stays together because it's a solid, and then we have magnesium chloride, which is broken apart. And so now again, the ones in red are the spectator ions. They don't participate in the chemical reaction. And so we can cross them out, and what we have left is the ions that participate in this reaction, which are the copper 2 plus and sulfide ions, to get copper 2 sulfide. So again, from the molecular equation, you break apart everything that's aqueous into their respective ions. Once you got the ionic equation, you look to see which side has exactly the same ions. Those cross out because they're spectator ions. They're not involved in the equation, in the reaction. Yes, and so again, whatever compound is, whatever compound is a solid, or it could be a liquid or a gas. And so there are some reactions we'll look at later that have a liquid. So if it's a solid, liquid, or gas, we leave alone. Only if it's aqueous do we break it apart into ions. So again, solid, liquid, and gas, you just keep it the same. You don't break it apart. Aqueous, you break apart. So we'll look at one more example. So here we have a molecular equation involving aluminum sulfate. Sodium hydroxide gives us sodium sulfate and aluminum hydroxide. And again, this is the molecular equation. And so the first thing we want to do is everything that is aqueous, and it's already balanced, everything that is aqueous, we're going to break apart. So here we break it apart, we get 2. So what I'm doing right now is writing all the reactants as ions because they're all aqueous. So there I've written all the, I've broken apart all the reactants because they're both aqueous. So I do the same thing for sodium sulfate, but again that 3 gets distributed to the sodium and the sulfate. And then aluminum hydroxide remains because it's a solid. And this is the ionic equation. So now you look to see what is exactly the same on both sides of the equation. We have 3 sulfate, 6 sodium, 6 sodium on both sides. So these get crossed out. And what we have left is the net ionic equation. So that's the net ionic equation when you react aluminum sulfate with sodium hydroxide. So in the next lecture, we'll actually be looking at a specific class of reactions called precipitation reactions, and we'll be using the net ionic equations to write the resulting reactions when we have a precipitation reaction. And so for precipitation reactions, it requires some specific criteria. We have to have reactants that are, 2 soluble ionic compounds react. So both our reactants have to be soluble for a precipitation reaction. So when you look at the reactant side, both reactants are soluble, meaning they're both going to have AQ next to them. And it forms an insoluble solid, which we call a precipitate. So on the product side, you need to have at least one compound with a solid indicator. So the 2 requirements, the minimum requirements for precipitation reactions, both reactants are soluble. On the product side, at least one compound has a S indicating it's in the solid state. And this is a subset of the broader group of reactions called double displacement or metathesis reactions. And so to give you the general form of this, double displacement means double displacement means you take the 2 cations and the reactants, you switch them to form 2 new products. And for precipitation, at least one of those products has to be a solid. So this is the general form of a double displacement precipitation reaction. You have two reactants that are aqueous. You take the cations, you switch them, you form two new products. At least one of those products has to be a solid. Now we'll see in the later lecture that you can actually have sometimes two products that are solids, but a minimum of one needs to be a solid. And again, the way we know which ones are solids is based on the uh, solubility rules. So for example, we look at this reaction here, silver nitrate plus sodium chloride gives us silver chloride and sodium nitrate. Notice that the two cations on the reactant side were switched to form the two products. So once you switch and form the two products, you would look at the solubility rules and you would ask yourself, is silver chloride soluble or not? If yes, you put an S. Then you would ask yourself, is sodium nitrate soluble or not? If no, you put AQ. And then from here, you can write the ionic and net ionic equations. So when you mix silver nitrate and sodium chloride, you'll see that you form a precipitate, silver chloride. And so again, this is what we'll be looking at in the next lecture, how to predict the products of precipitation reactions, which means we'll be looking at the solubility rules. So if you have time between now and the next lecture, make sure you go and kind of just look over the solubility rules in your book, because that's the one we'll be using, and that'll help you predict the precipitate in precipitation reactions.